try to show you some, I will go to a much lower scale compared to what Jan presented this morning. If he was speaking about tens of kilograms, I will speak more of milligrams. So I go really to the carbon science and carbon science. I will try to show you some important properties of biochar, and one of the great challenges we have now with this kind of material is the characterization of the material itself. And I will try to use it in relation to catalytic properties because it is a good example of an application in which structural, chemical and textural properties are strongly related to the performance of the material, and these properties are quite difficult to analyze on biochar. So first, I'm coming from, to present me a little bit more, so I'm coming from Mulhouse, which is in the east of France, obviously extreme heat, close to Germany and Switzerland. And I work in a CNRS University mixed lab, which is around 200 people and 60 PhD students. And we work on material and especially on interaction of material with the environment. So we deal with surface, interface, and we try on improving materials by tailoring surface porosity, surface chemistry, and so on, with many applications and polymers, carbon materials, of course, and biomaterials, and so on. So don't hesitate to go to our website to see more data. So what about carbon research? We are nearly 2 teams working on carbon material in our lab, and we work mainly on synthesis of carbon material, mostly from bioresource, with controlled structural, chemical, and textural properties, and more by adding also some heteroelements. It's more important in our for characterization, we have specific system in our team, but most of the work is also done on a technical platform, which allow us to do a lot of work in any case. The applications are, for a great part, electrochemical energy storage. I won't speak about that, it's not my team. I will deal with my work, which is more biochar, with mainly lab scale, but also small pilot scale that we have in our lab. I will speak about catalytic application because it is the main part of my application for now in this area. But I've done a lot of work also on adsorption before. The other part is carbon-carbon composite with work with industrial partners on industrial electrode, aircraft brake, and so on. And again, in this work, we are working more and more with including how to include biochar, especially in electrodes. There is a lot of work at industrial scale to try to include some biochar. So I will come to the carbon itself. So my work is carbon material. So when we look at carbon, the base is a graphite, which is shown which is shown here. Coming to more real carbon, actual carbon, we have 2 ways to see them. The first one is illustrated here by pyrocarbon. It's a model of pyrocarbon which was done in another lab in Bordeaux, which shows that we have mainly aromatic cycle. And what is shown here is that we have a lot of stacking, graphene material, nearly graphene sheet, and a lot of stacking, but also that we have in blue what is shown to be nearly graphene-like material, but in yellow you see what are known as defect. Now, defect can be many different things. It can be for example, what we call a stone whale defect, which is just a small defect which will have no influence on the reactivity of the material. But some defects, like the edge or lacking atoms which are lacking in a cycle, will lead to vacancies, low coordination site, free valence, and all these defects, edge atom, dislocation, and so on, are what we are looking for, because it is where we have activity. On this defect, you will have also potentially some heteroatom, which will lead to functional group. The most current, the most often observed is of course oxygen, but we can find also, for example, we can add some sulfonated groups to change the surface chemistry. Of course, these functional groups are strongly related to the structure of the material, since they will be grafted on the defect, the structural defect. Of course, we can add more and more hetero elements, which may be catalysts, promoters, inhibitors. We have endogen elements or added elements, which are metals, alkaline or alkaline plus metals, silicon, phosphorus, and so on. So all this make some carbon material. If we come to what we expect to be an activated carbon, it's much more complex, because here, for example, you have a model which was done in USA some years ago, which is obtained by Monte Carlo simulation. And we see that we have an isotropic material which is nearly homogeneous without any stacking. And so it doesn't, this model failed also since it doesn't take into account the actual structure of the carbon material, which should be between these two, between pyrocarbon and activated carbon. Since we know we have some crystallites which are not graphite but more pyrocarbon with some structure, and some amorphous part which is related to activated carbon. So all the reactivity and the surface chemistry that we have is related to this structure. So how to analyze this? First thing, when we look at surface chemistry may be of importance in catalytic application, depending on the temperature. Here you have an example of XPS analysis on the O1S peak. It's quantitative XPS analysis. It was done with in-situ heating and, in our XPS, and analysis in exactly the same condition. And then we can compare the intensity. And we see that we have a decrease of this peak from up to 900 Celsius degrees. Not only a decrease, of course, which is known, but also a change of the shape related to the change of the surface chemistry. This can be compared with temperature program desorption with some mass spectrometry analysis, which allows us to follow the functional groups which decompose as a function of temperature. So we can compare the two and see that we have, of course, the water which is evolving, which is related to mainly to hydrogen bond. But also then we have CO2, which is removed related to carboxyl, and then we have lactone, semiquinone, which will lactone and anhydride and so on, which will be removed, and then we have semiquinones at high temperature, around 700, 800. So that shows that depending on your application, you will not have to deal with the same surface chemistry, whatever you have done with your biochar. For example, with moderate temperature reaction, pyroforming, water gas shift reaction, for example, you may have to work at 300 or 400 Celsius degrees, maybe lower, and then you will have a rich surface chemistry with acid group and many oxygen-containing compounds. If you go to bioenergy, for example, for thermal cracking to produce hydrogen, reforming, and so on, you will not have any more chemistry, except, for example, some semiquinone which are present and stay until 800 Celsius degree. So you will have to work not with the surface chemistry, but with the structure of the material, that is the active type. So for this, the advantage to say about chemical analysis, it was shown that XPS, doing quantitative XPS is huge work. It's complex, but temperature current desorption give a quantitative analysis if you are doing some good work, which allow you to follow very precisely the surface chemistry of the material. So you were able to do that, and it's very efficient and very reliable if you do some good work with your material. So I will show some results which were obtained in the frame of, mainly in the frame of screening of different biomass that we had to do for the French Agency for Environment and Energy, in which we use classic lignocellulosic resource like wood, different wood, but also many byproducts like crop residue, animal manure. I will show some of them. Not all, of course, with of course only different composition, mineral matter, and so on. So the furnace used was at a gram scale. It is interesting to have this kind of furnace for two reasons. The first one, you see that it is a furnace in which we are able to introduce, to preheat the furnace and introduce, if we want, the sample, the biomass. It allows to have either a slow pyrolysis or fast heating pyrolysis. Slow heating if we put the biomass in the furnace and heat the furnace. Fast pyrolysis if we preheat the furnace and insert the biomass inside. The second aspect is that working on a very low scale, 1 gram, for example, 2 grams, a few grams, we avoid most of the secondary reaction between the volatile matters and the char. And this allows to have very reproducible biochar. We can do many experiments and we obtain exactly the same thing. So it's very valuable for this. And an important thing also is that we have observed that it compares well with our small pilot plant that work with nearly 1 kilogram per hour. And then we do some all the characterization. So coming back to the first one, which should be quite obvious for us, is chemical analysis. So I show only one lignocellulosic material, and you see corn crops, which are actually used already for many studies. Digestate, so solid digestate coming from a local industrial partner. Poultry dropping, cattle manure, so many different materials. The first thing that will be of strong importance in our case is the fact that we have a lot of mineral matter. In lignocellulosic material, often we have nearly below 1% of mineral matter, so it is not of strong importance. And then we see that for byproduct, we have up to 14% of mineral matter in our material with very changing elemental composition, so which was obtained by, for example, by X-ray fluorescence analysis. And we see that, for example, for corn crops, we have nearly, it's a small amount of mineral matter, but mainly with potassium, calcium, and so on. But coming to the other byproduct, we see that we have a large amount of silicon, of phosphorus, of course, but also a large amount of potassium, calcium, and other alkaline earths. So very different kind of analysis, and especially for catalytic application, we know already that, for example, potassium is a good promoter for many catalytic application or many catalysts, or silicon and phosphorus may be more known as inhibitors. So this is of importance since we are always doing mass balance. Mass balance is a challenge with biochar. I show here again the same result. So it was obtained for fast pyrolysis at 500 Celsius degrees, and we obtained generally larger amount of biochar, the red line, with byproduct. You see up to 14%, which is a huge amount compared to what we obtain with lignocellulosic material. So this is a good thing. Of course, a large part of this is related to ashes, to mineral matter. And we see that we have in the biochar an increased amount of mineral matter. If we assume that the immediate analysis that we have done here is good, we can calculate that for all these materials, the ash yield, the transformation, the ratio between the ash we observed in the biochar and the ash we had in the pesticide material is strongly different depending on the material. For example, here you have for corn crops, for Douglas it's too low, so it's not possible to analyze it, but for corn crops, nearly 50% of the pristine mineral matter is converted to ashes in the biochar. It's much more important for digestate, and again, up to 80% for poultry dropping and cattle manure. This is of importance for all mass balance, and it should be related to the analysis. If you go to the analysis, you see that in our poultry dropping, for example, and cattle manure, we have a lot of silicon, for example, and phosphorus, which will be kept in the mineral matter, compared to digestate or corn crops, which has a much lower amount of silicon and phosphorus. So this shows that you have to take into account the composition of your mineral matter to understand the fate of ashes in your material. An important thing is that if you go to the other mass balance, which is a part of the organic part, that is the fixed carbon and the volatile matter part, you see that you obtain a higher amount of carbon yield compared for byproduct. So that shows that the mineral matter has an effect, which is a well-known problem that we have in pyrolysis, in bypass pyrolysis. It shows clearly that the mineral matter has an effect and seems to increase the carbon yield when you use byproduct. So let's go to the structure. Structure is a challenging thing for biochar. As I said, Anthony showed yesterday some experiments that we have done with solid-state NMR. Solid-state NMR is interesting, but we work at bond level. Bond level is a functional group, and to observe functional group easily in biochar, you have to work up to 400 Celsius degrees, for example. At 500 Celsius degrees, the amount of what you observe is, it's very difficult to observe nice NMR peak, so it's more complicated. There have been a lot of development in Raman spectroscopy. Raman spectroscopy is interesting because it works at a higher scale. We all know the D peak and the G peak. D peak is related to what we call polyaromatic with defect, and G peak without defect, which is of course false. But anyway, what is interesting is that this peak, the difference of with defect and without defect, is interesting since from the theory, from what, for example, Andreas Farabi has shown, is that what we call defect for Raman, for the D peak especially, is to have some kind of density of defect on a given surface. And this gives access to some nanometer scale, which is not possible to obtain by NMR or by X-ray diffraction. This is very interesting. So the D peak shows that you have a graphene with a density of defect which is relatively low, but at the scale of 1 nanometer, 2 nanometer. If you have one defect every 4 nanometers, you will come to the G peak. You see? So it's very interesting because it gives access to the mesoscale of the material. And anyway, when you go to, so for carbon obtained at 800 Celsius degrees, you see it's very interesting that it's very easy to analyze. We have 2 peaks and let's go, you can do different models. Coming to most biochar, which are around 500, 600 Celsius degrees, it's much more complex because we see that we have more satellite spikes, which are related to some kind of bond, showing that there is already some oxygen with the ether bond, or some defect which shows that we have double carbon bond, or CH, methylene, asymmetric array, and so on. So the decomposition of this spectra may be challenging. One easy way to do it is to work with the haze of the 2 peaks. It's not very nice, you can do better, but it can avoid also some errors which are done with a more complex model. So I've done that, and we obtain that. This kind of result. We see that, of course, if we increase temperature, we increase the ratio of D to G. The peak D shows that we have more and more graphene layers which have some defect. So it's really strongly related to carbonization, which is logical. So we increase this ratio, so it's okay, this is well known. We see also that there is some effect of the heating rate, which is more complex to analyze, of course, but we see that increasing the heating rate, going to fast to slow. Fast is nearly some 50 Celsius degrees per second, and slow is 10 degrees per minute. And so we see that by increasing the heating rate, in most cases, we have an increase of the carbonization level. So this may be related to an increase, a more quick evolving of the volatile matter and release to secondary reactions. So Raman is very nice to analyze the structure. I will not spend too much time on textural properties because it's also a complex problem. We use generally nitrogen at 77 Kelvin. UPAC shows that, propose that it should be the standard to use argon at 87 Kelvin, but it's more complex, it's more expensive also. We observe generally that it is very difficult with biochar, especially low temperature biochar, and often we use CO2 at 0 Celsius degree. Here I show the result obtained for some material, which is what we observe is that with biochar we have a very low surface area. It's only pristine material. So this material itself is not usable for most applications that we are interested. And this is of importance since, as it was shown before, for example, in the previous publication, we need to do some more treatment, which are known as activation in many cases, but anyway, it needs more treatment, so it's not a good way to work. An important thing, so this is very important, and we see that for all materials, all biomass with a lot of mineral matter, we have a very low surface area, and also a very low micropore volume, which was measured by CO2. So we have a strong difference between these materials, and this is a limitation for the application. So to see some example of all this, I first begin by CO2 gasification, which is important, of course. So we know that textural properties and so on are of importance, but here I show the influence of the mineral matter. I will focus more on this. So here you have some material which were model material. We have doped the material with different amount of potassium and silicon. which are known as catalysts or inhibitors. And what we see is that when you have a material which has these elements, on the left you have the effect of potassium. We see that when you have 2%, for example, which is a classical amount, up to 60% of acidification, you have nearly no effect. It is only when you go to the high conversion ratio that you see a strong difference between the effect showing the catalytic effect of potassium. It is the same when you go to silicon and inhibition. Up to 60%, you have nearly no effect of silicon on the gasification. At above this value, you have a strong decrease of the reaction rate related to the presence of this silicon. So it shows clearly that you have an effect inhibiting catalyst, but also that this effect is strongly related to the amount of materials that you have compared to the amount of carbon.
I request you to kindly.
So I will be quick.
Sorry.
So I skip this. Just this one is fun. So just to show last example, it is related to hyperaccumulator plant. This one was what we call Alison Morale, which is grounding on ultramafic soil in Albania. And this soil contains nickel. And in the plant we have between 0.5 to 2, it depends of if you look at the whole plant or if you some specific part of the plant, 0.5 to 2, that's 8% of nickel. So you have the chemical analysis showing the amount of nickel. You see in the seed and in the plant, the full plant is different. So we have worked with the full plant because it had no sense from an industrial point of view to work only on the seed. An important aspect is that the speciation of nickel is of importance. So of course, when you use some XPS analysis, we see that we have nearly all which is present as nickel Ne2, either from on the form of oxide and different other compounds. Doing ADX and with MEB, we see that we have different elements in our biomass, which are the small stars are called trichome, and they are mainly, you see, some saline elements which contain carbon chloride and things like that. No carbon, calcium chloride. And we see that the nickel is strongly, very well dispersed in the biomass. Into the biochar that we obtained with this, it was done at 800 Celsius degrees because we want to use it for dry reforming. We see that we have, again, a very low surface area of the material, very low porosity, so we have to activate it to obtain a good material. And the second aspect is shown with the XPS analysis. We see that we have changed the speciation of our element. We have already some part which is related to the peak, the left of the peak of the left, which are nickel 2, but we have also nickel 0, which is coming. Which is the right part, the blue peak. This is also strongly related to the surface chemistry. If you have a lot of oxygen on the surface really, of the pristine material, of the biomass, you will have more oxygenated material. You have a low amount of oxygen in your pristine material. During the pyrolysis, you will produce more nickel 0. So the speciation will change during the pyrolysis depending on your biomass. So we tested that for dry reforming reaction, and we obtained an interesting good catalytic efficiency. Of course, we have deactivation, which is often observed, always observed in such a reaction, but it is limited since we use dry reforming, so we have CO2 gasification of carbon. And we observe also, as always, with nickel, Oswald recording, which show an increase of the particle size. You see the light on the right, the change in particle size distribution of the material. So this is classical, but it shows that using the endogenic element may be of interest and may help you to obtain biosourced material here catalyst, in a one-step way. So to conclude, biochar are obtained from many different resources. Chemical analysis is challenging because of the fate of mineral matter is not well known, and it should be known, but only if you know everything about your mineral matter, which is very difficult. There is a very strong structure-reactivity relationship, which is complex to analyze also. Raman is a good way to do it, but it's not obvious. In fact, you are characterizing defects, so it's not so easy as to do. Development of porosity is well known for industrial material, but it's much more difficult for biochar, which are related to byproducts with high amount of mineral matter. And for synthesis, of course, the simplest is the better, so as well. And I showed you some application, and sorry for being a little bit.
No problem. Thank you.
Long live India and France friendship.